Okay, thank you, everyone. Yeah, we're getting very low in the stack here. Here, I had an introduction slide for myself that covered pretty much what he just said. I've also built a couple apps. I used to be really active on Stack Overflow, although that's kind of died now. And I maintain a couple packages that are somewhat useful, and I think I will probably actually be translating to using FFI when I have time after this talk, because honestly, it's pretty good, the stuff that I've been doing with it. So the outline for my talk today, we have the 5 W's of FFI, when you're going to use it, where you're going to use it, how you're going to use it, the way to integrate a C library into an application that works cross-platform across all the platforms that Flutter supports, except for web, and then tying up the loose end of web. And then we're going to go through a little bit of an audio project that has a little bit deeper integration into Android and iOS specifically. Then there's learnings and summary at the end. So who is FFI? Wait, that doesn't make sense. How plugins used to work. Let's talk about this a little bit. So way back in the day, Flutter had message channels. It still does. A lot of the plugins you use will be based on message channels, which are essentially just passing information back and forth in a somewhat structured way between the operating system and the Dart runtime. It's manual, it's slow, it's error prone. There's things that can go wrong with it, although they do work pretty well once you've tested it at all. Then the Flutter team came out with something called FFIGen, which you can basically structure the type of information that will be passed back and forth the message channels. It helps. It does some helps with making it so there's less errors and automate a little bit of it. It is still slow, though. And then finally, they did have eventually an FFI package, which was really good, but it was still manual doing all the coding. You'd have to check all your types manually, and if you messed up, then the whole thing would crash a lot of the time, rather than just having an error because you're touching the native system. So now we have automatic FFI using FFIGen, which is most of what we'll be talking about today. So what is FFI? It stands for Fast Foreign Interface. Originally, Lisp had it in their programming language, and then it's been translated all sorts of other places, called slightly different things. Like in Java, it's called JNI. Python has CFFI, depending on which Python runtime you're using. And essentially what it does, it'll let you use Dart code to talk to C libraries, Rust, C++, whatever can expose bindings in a way that is understood by Flutter, which is C bindings. So now you can have build hooks to compile your code into the libraries for each platform. You have automatic bundling for the different operating systems. You have code inference and code generation, which mean you don't have to write all that glue code. It kind of just happens automatically. Why would you use FFI? Well, if you need more performance than Dart is capable of, this is your tool. You can push it into Rust or C. I will say Dart is capable of more than what people use a lot of the time, so you could actually optimize in Dart as well. But we won't talk about that in this talk. If you need access to operating system functions, then you have to use FFI or message channels. If you need advanced threading, locking, so if you have to have things happening in different threads, Dart has isolates, which are powerful, but not as powerful as threads, and it's not something exposed by the Dart engine. And a lot of the time, there's something that already exists in a different language. You don't want to have to rewrite OpenCV. It's a massive undertaking. People have tried in all sorts of different ways, but it never really turns out as well as OpenCV because some people have poured, millions of hours into this open source library. So some examples: OpenCV, SQLite. Sodium is an encryption library I use fairly often. When not to use FFI, well, so if you have an existing library in Dart, it's not going to normally be that much better to go into a different language. If you're doing a lot of tiny little operations, there is still some overhead with FFI, so you don't want to be doing, A plus B on, calling off to the operating system to do that. That's crazy. Just do it in Dart. It'll work. And if you can do optimizations in Dart, it's probably better to start there before making a whole bunch of extra potential things to go wrong, which could in FFI. Some of the optimizations for Dart, you can use SIMD in Dart, caching, pooling. Some disadvantages of FFI is that debugging is quite difficult. Things will just go wrong. Things will crash. you are kind of putting yourself in a little bit of danger as soon as you touch FFI, because you're not in Dart's nice little sandboxed area where when things go wrong, it just throws an error and keeps on going. This will cause a crash. You have to do manual memory management, which if you are a C programmer, you'll be aware of. If you are not a C programmer or C++, there's a lot of pitfalls that you can make, and this just exposes you to all of them. And same thing with threading. So there's some places that FFI is already used, SQ Flight. I won't say them all, but these are some libraries that use it already. And I think some of them use the older methods. Some of them have migrated to doing this newer way, which is exciting. So the first example I'm going to do is for a very simple cryptography library called MonoCipher. It does, if you want to do secure communications, it's a really simple way to do it. It's a single C file. You don't have to have a bunch of dependencies, so that's why I chose it for this example. It compiles on every platform. It's easy to use. So to compile it is actually quite simple. So in the root of your Flutter project, you just drop monocipher.c, monocipher.h. Then you have to set up an FFIGen code, a template here. This basically what it says is this is where you find the header files. That's going to tell your program how to talk to the library. And it's basically just what you need to do, something like this. And then this is telling it where to output the code. So you'll have these generated bindings, which let you call from Dart code directly into the library. There's also a way to do this. The newer way to do this is actually using a Dart build file that you put in a tool directory. This has all the same things. It has the header file that is reading to find the code. You do have to do a little bit more work to tell it exactly what to include and what to exclude. So that you don't want to necessarily generate code for every single function in a C library, because sometimes they have thousands. You might only need 3 of them. So you can kind of pare down your code a little bit that way by specifying things. And then when you run this, it outputs that Dart code. I haven't actually included an example of it, I realize, but it's kind of ugly, it's messy. You don't really want to look at that anyways, you just want to use it. And then we have the build file. So they call this build.yaml, it's actually build.dart. This actually compiles the C code as part of the Flutter build. So you don't have to do anything extra. When you hit Flutter run on your IDE or on the command line, it'll actually use a C builder. That's something that the Dart team has built to compile this C library, bundle it up for all the different platforms, and include it in your application. So you don't need to worry about frameworks and SO files and all the other kind of stuff that was really a pain in the butt when you wanted to do anything like this before. Then these are the bindings that it generates, or that I have written, to touch those, to use those, that code. It's quite simple. You have to do a little bit of things to, so say for example, is this one. We have some translation between the FFI layer and Dart, so making things into FFI pointers, which is a pointer to memory that can be passed to the C code, and then translating it back. You have to do memory allocation, so that's what this malloc function is, which is provided by the FFI library. And then when you call the native bindings, it's simple. It's Dart. You just have to make sure that you get the right types, and then things just work. It's compile safe. I'm sure you could break it somehow. I haven't managed to yet. And then the result is that you have a program that can sign messages. So let's say hello Flutter. We sign this message and checks. It creates this signature and then verifies that the signature is correct. So this is actually calling into MonoCipher right here. I decided to write this whole presentation in Flutter because I'm a little bit insane and wanted to see if it would happen. So it's working. That's good. There was a risk it wasn't going to. So we've talked about the native platform. For web, you can do more or less the same thing. It is a little bit more complicated. It's not directly FFI, but it's kind of similar. What I've decided to do for this is show you guys how I got MonoCipher to work on the web as well. I used Clang to generate a WASM block. So for anyone not familiar, WASM is WebAssembly. it allows you to run C programs or other programs like that in the web. There's a little bit of work I had to do extra to get allocation to work there properly. So this is something that eventually will be included. For now, you kind of have to do manually to do memory allocation in WebAssembly. It looks ugly. You can get Gemini or something like that to generate this just fine. It does a good job of it. And then you have to do a little bit of initialization on the web. It doesn't work quite as seamlessly. You have to load the WASM file and then instantiate it, but relatively painless. This looks very similar to what I did with FFI, but now we're just calling 2JS on these web crypto pointers. And we can do the exact same thing as with FFI and have this library working on web as well. So, oh, that was it. OK, I thought I was going to have an example, but I did not. So it's the same as before. I can show anyone else who wants to see it afterwards running on the web if you like. So yeah, that's it. So that now we have covered every platform that Flutter supports. You can have a cryptography library that works across every platform with, floor configuration files, drop in the C libraries, and have it work everywhere. So I really think this is something really powerful that Flutter has been missing for a long time. And I'm actually going to explain how it gets even more powerful in the next little bit, where we're going to talk about a little project I made to stream audio directly from the microphone of your operating system. So on iOS, it uses AV Foundation. Android uses Audio Recorder. Web, desktop. Desktop, it uses a little library, header library called Mini Audio that you can just drop in. And it captures audio bytes directly to a stream that you can then do all sorts of calculations on. This is the Dart file that I've made here. So basically, you have a start capture, stop capture, and a stream that just spits out bytes of data. Because it's just one single microphone, it's not going to overwhelm your system. If this was images, you'd probably need to do a little bit more memory management because it would just overflow. On desktop, it's as simple as dropping in, similar to MonoCipher, miniaudio.c and miniaudio.h. There is a slight little thing there. When Dart compiles C code, if it has untyped enums, Dart doesn't know beforehand what type of integer it will be when it compiles. So in one system, it could be an int16. Another system, it could be int32. So you might have to go through your library and make some small changes to enums to define what size they are, because otherwise you'll have a fun runtime crash that you will have no clue what happened. It just won't work. And you're like, why did that happen? You can also, let's see here. What was this? This is the header file showing the enums. This is what it was before. I wrote a little script that just changes that to typedef uint32 so that FFI knows how big the pointer is. For building, this is just kind of paring down this file to only the things we need, but similar to the MonoCipher one. And then the result, if this works, oh, there's something in my screen here. OK, this is pulling from the microphone, and you can see it's measuring the loudness in the room. I'm not going to try singing because no thanks. But it technically measures pitch, not very well. Well, I could try. Did it just crash? No. Has the frequency spectrum and an oscilloscope that shows as things are going. So if you clap, you can see it go really crazy. Now this is running over a Teams call on my computer. It actually runs perfectly smoothly. But yeah, if you want to play around with it afterwards, I can show anyone who wants to see it. I'm going to just stop it before I go to the next page because I wrote this very quickly and it might not do deallocation properly. So that's the application. It works. That's running on my Mac. That's a Mac application running on my Mac right now. This whole presentation is a Mac application. To work on Android, you use something called JNIGen, which is kind of like FFIGen. But what it does is it interfaces directly with Java and Kotlin. So you can generate bindings. For this case, we generated bindings for audio record, audio format, and media receiver, which are the three things you kind of need on Android to be able to record audio. A little small wrinkle is that you need to have the audio capturing come onto a new isolate. because otherwise it just kind of breaks things. But that's relatively simple to do. We'll see here. This is the configuration for generating the bindings for these 3 libraries. And you don't really have to do anything more than that. It already knows where the Android's SDK is, and it'll just generate what you need to be able to call directly into it from here. We have an isolate set up. If you've done any isolate work, this will look familiar. It's just kind of passing things back and forth. On the recording end, these are all calling actual Java functions and using things directly from Java. So you have the encoding mode, mono, get, min, buffer. These are things directly calling into Java. Start recording, and then we have a loop, which just reads out of the buffer, copies it into a float32 list so we can deal with it in Dart, and then passes it off on the stream and does stuff to make sure that it doesn't block completely there. So that's Android. That's it. For iOS, well, it seemed like it was going to be just as simple. Unfortunately, it's iOS, so it wasn't. Kind of similar idea. We start with using FFIGen. We pull in AV Audio Engine, AV Audio Node, a bunch of different audio things from AV Foundation that is built into the platform. It kind of figures out, you have to put in the paths, but it can just pull directly from what's already on your operating system. You don't have to download anything. You have it spit out bindings, and then to run, these are actually calling in similar ways to what we did with Android. These are actually calling like AV audio session.shared instance. These are things that are calling directly into like the Apple ecosystem. And theoretically, it should just be this simple, but of course it isn't. The problem is that the way that the audio engine works is it actually spins up a new thread and spits out all of the data back onto that new thread for performance reason. It makes sense for Apple, but Flutter does not like it because you're trying to marshal across a boundary it's not really happy with. I think that the Dart team is working on something for this, but it's not there yet. So we have this marshaller.get bridge block, and I will explain what that is in a second here. This was what I spent all day Sunday working on because it was not working on iOS. Basically, this is the callback. This block here is it's calling back into the Flutter code, but that was causing a crash. So instead, what I had to do is make a marshaller. It's relatively, not that complicated. Basically, what this is all saying here in this gobbledygook, I don't really like Objective-C particularly. So what it's basically doing is you're passing a callback to your thread in Dart. Then you have a buffer, and then let's see here. What else do we do? Sorry. Yeah, you initialize it with the Dart callback, and then you have this way to get a block, which is what you pass to the audio initialization function, so that when it calls back with buffered audio, it gets passed into this. Now we'll look at the implementation file. It's basically just pulling this buffer out. It's copying it into some memory that it controls, and then pointing it off to Dart, so then we can deal with it in Dart. And then if we do that, then things kind of work. Oh, sorry, I just forgot to mention here, you have this dispatch async to main queue. What that is doing is it's pushing the operation here back onto the same main thread that all the Flutter UI is running on for safety. If you don't do that, then this whole thing breaks. I had to figure out how to get this file to compile. This is me inserting it into the code generation. So the code generation looks at this header file that it has created and pulls out that class. And then the compilation, specifically on iOS, is relatively simple. But if you don't have these little flags here, then it will look like it's working, but then fail at runtime for unknown reasons. And the documentation for this is still a little bit rough, just because there hasn't been that much done in it yet. So trial and error, eventually figured that out and got it to compile, got it to lock in. And then after that, it was kind of as simple. Oh, sorry, no, that was it. It was simple as just using it in the code here. Sorry. Yeah, so marshaller.get bridge block. And install tap on bus, that lets us pull the audio buffer from the microphone. Next, I just wanted to talk slightly about web. So once again, I wanted to make this work on web as well because I'm a bit of a completionist, even though I didn't actually need to do any of this for this talk. But in web, you don't need FFI at all. You don't even need to have anything compiled out externally. You can just access the existing things in a web browser through JS-interop and the web package. So you can get audio context, media stream, analyzer nodes. This allows you to pull out those buffered pieces of audio and then pass it back into Dart the way you would for the rest for every other platform. So we basically, you have analyzer, you have a you have a timer that basically runs every 16 milliseconds, pulls the audio, and we'll look at the pull function here, where it's just getting, some float time domain data, which is, fancy words for the wave of audio coming off the microphone. And that's it. So it works on web as well. So I've talked about some of the issues I ran into. There's threading on iOS that is just not really quite there yet that the Dart team is working on. You can't control which threads and which isolates you're using really yet, but I think that will come soon. The other thing is that doing this, because of going through those different threads, there's actually a couple copies of the audio as it gets processed, which is not ideal. Like if you're really doing some real-time stuff with audio, you wouldn't want to do that. What you would actually probably do is push your implementation code directly down to the platform. So you'd have your FFTs, like whatever processing you do in Swift or Objective-C, and then just get the results back in Dart using the same way. So you could use what I showed you there with having the Objective-C code as well as the Dart code, mix them together, and be able to do all of what you need. And the Objective-C is awful. In real life, I would actually probably just use the Minio audio library everywhere because it actually handles iOS and Android specifically. But for the point of this talk, I really wanted to get into the nitty-gritty of how it works on every platform and also show that you can integrate something into iOS and Android without having to have pretty much any external code at all. That's basically, I mentioned the processing already. There's some future stuff. FFIGen, I wanted to include that in this talk, but I ran out of time. And what that does is you can actually have Swift code that instead of using Objective-C, so it's a bit nicer. There are some huge caveats, and it's very experimental right now, so I wouldn't plan on building anything in production with it, but it's coming soon. The other thing is that with FFI, it's really powerful, but if you wanted to do anything with a platform view, so say if you wanted to have a camera running and process frames in real time, it's not really well defined how to do that with FFI yet. I think you can make it work, but it would be a little bit complicated passing pointers back and forth between the old way of doing things and the new way of doing things. And that's it. Yeah, we talked about compiling scene plays using FFI to generate bindings, JNIGen on Android and FFIGen on iOS. If you want, this whole presentation is on GitHub. I can, this is for the monocypher integration. And then this is for the FFI presentation. If you want to take a look at the source code, it's all up there. I can put it up. Or if you want to talk to me afterwards, I can just give you the link. So that's it. Yeah.
Thank you very much, Logan.